expansion work of a system being compressed. When a system is compressed, work is done to the system, and therefore the sign of the system work is positive as the system gains energy from its surroundings. Quantitatively, we use this same equation for work. And by convention, although this is a compression, we still call this work as expansion work. Numerical examples here. Let's calculate the system work in the following isothermal processes. Process A. A 80-liter ideal gas with initial pressure of 1 bar is compressed to 20 liters by an external pressure of 4 bars. So how do we compute the system work? Work equals negative integral P external dV, and P external is a constant, so we can take it out. It's 4 bars, and the final volume is 20, initial volume is 80, so we have 20 minus 80, the total will be 240 bar liter. And this is a positive number, as the surroundings does work to the system. Now let's look at a two-step process. Let's say still we have an ideal gas with an initial volume of 80 liters and initial pressure of 1 bar. Now it's compressed to 40 liters by external pressure of 2 bar first, and then further compressed to 20 liters against another external pressure of 4 bars. So if you look at examples A and B, they share the same initial condition, 80 liters, 1 bar, and they share the same final condition, 20 liters and 4 bars. But in example B, we have to look at the two steps separately. Step 1, the external pressure is 2 bar, and then the volume change is negative 40 liters. Therefore, the work done to the system is 80 bar liter. In step 2, the external pressure is 4 bar. The volume change is negative 20 liters. And then the work done to the system in step 2 is 80 bar liter. In sum, the total amount of work done to the system is the sum of W1 and W2, which is 80 plus 80, we have 160 bar liters. This is smaller than this 240 bar liters. Let's visualize this process. So let's say if we first use a constant external pressure of 4 bar and then compress the system from 80 liters to 20 liters. So really we go from here to here, and then the amount of work is the area of this rectangle with two sides. One is the external pressure of 4 bars, that's the height, and this width is 60 liters. Therefore you have 60 liters times 4 bars, you get 240 bar liters. However, in a two-step process described in example B, we compress the gas first against 2 bar by a 2 bar external pressure. So really in step 1, this rectangle area corresponds to the amount of work, which is 2 bars times the difference of the volume 40 liters, so we get 80 here. And similarly, we have 4 bars times 20 liters, also we get 80 bar liter here. And in sum, the total area of the two rectangles is 160 bar liters. So what's the difference? The difference is this rectangle here. Okay, this is missing in the two-step process. In the one-step process, the system expands against the 4 bars from 80 liters to 20 liters, so we need to include this rectangle, okay, which is actually 4 times 40. I'm sorry, which is 2 bars. So 4 bar minus 2 bar, which is 2 bars times the difference between these two is 40 liters. So there's a area of 80 bar liter not being covered in this example B. Therefore, these two numbers differ by 80. So the point is, if we design a multi-step process, the amount of work done to the system may be smaller than the one-step process. So can we further decrease the amount of work? Yes, of course. So we don't have to kind of compress the system by 2 bar pressure first, because the initial pressure of the system is only 1 bar. So why don't we use just 1.5 bar external pressure to compress the gas? So we use 1.5 here and then compress the gas, and then we get this rectangle area. And then we use 2 bars, and then we get a second rectangle here. So look at this. If we design a 3-step process using 1.5 bars, and then 2 bars, and then 4 bars, actually we can further reduce the amount of work by this much. It looks small, but this is non-zero. The area of this rectangle is actually this side, 2 bars minus 1.5 bars times this volume change. So again, although small, it's non-zero. So by designing a 3-step process with P external equals 1.5 bars, 2 bars, and then 4 bars, we can further decrease the amount of work done to the system. But then is there a limit? Can we just decrease the amount of work to 0 or indefinitely? There's no way, because to compress a system, P external must be greater than P. So this system pressure P serves as the lower bound of P external. So over here, this is the system pressure using PV equals RT, the reciprocal curve here. So P external should be greater than P. Therefore, the minimum amount of work we can achieve is the area under this reciprocal PV equals RT curve. So let's look at the third example. Again, a 20-liter ideal gas, P equals 1 bar, is compressed to 20 liters by P external equals P. Alright, so initial condition is 80 liters, 1 bar. The final condition is 20 liters and 4 bar. So how can the gas be compressed if P external equals P? If P external equals P, the system can not expand or be compressed. But you may imagine P external is slightly greater than P. What's the difference? 10 to the power of negative 1000 bars. This amount is so small that we can still say P external equals P, and yet we can also say P external is smaller than P. It's a mathematical trick. And then how can we compute work? Again, we use the initial equation for work. This is the original equation for work. We always use this equation to compute work, but in this example, P external equals P, so we replace P external with P, and P equals nRT over V for the ideal gas, and then we can integrate this nRT over V. We get negative nRT times the natural logarithm of V final divided by V initial. And because it's an isothermal process, we can use initial PV or the final PV because the temperature does not change. Therefore, the product of PV does not change either. And then the initial PV is 80 bar liter. The final PV is also 80 bar liter. And then we plug in the numbers. We have this 80 bar liters times 1.386. This is Ln4. And then the result is 111 bar liter. That's the minimum amount of work done to the system when this ideal gas is compressed from 80 liters and 1 bar to 20 liters and 4 bars. And then we can visualize this amount of work. We go from here, 20 liters, 80 liters and 1 bar. That's the initial condition. We compress the gas to 4 bars and 20 liters. This area under the reciprocal curve is the amount of work, 111 bar liter. When a system is compressed by an external pressure with the same value as the system pressure, the compression is called a reversible compression, and the amount of work done to the system reaches the minimum.